To understand how AI learns, we first have to look at the baseline. Current language models are trained by reading massive amounts of static text to do one thing: predict the next logical word in a sequence. This high-volume autocomplete process works well if you want a model to write a sonnet or retrieve a piece of trivia. But guessing the next word breaks down when a task requires long-term strategy or adapting to a situation that changes with every move. Most models rely on a simple mathematical rule called cross-entropy to measure how well they guess the next token. However, writing an equation that captures subjective, high-level goals like strategy or creativity is considered an intractable engineering challenge. To solve this, researchers realized models needed to stop passively reading historical text and instead start actively interacting with environments. Shifting an AI from passive text prediction to active environment interaction provides the framework needed to build agents that can navigate complex, multi-step tasks. We can see this in practice by dropping a language model into a specific, testable environment, the text-based game of Wordle. Before its first guess, the model relies on its policy, an internal rulebook deciding which 5 letters to play. The agent then performs a continuous rollout. The environment provides feedback, green, yellow, or gray, which the agent uses to inform its next move. Completing a full rollout forces the AI to be an active participant. It has to react to the real-time consequences of its own decisions. This meter visualizes the reward phase. Once the rollout finishes, the environment evaluates the final state and assigns a numerical score, like a 1.0 for a win or a 0.0 for a loss. In human preference training, which is used for chatbots, this reward score comes from a separate reward model, judging the overall quality of the response. To process these rewards and actually improve the model, researchers use a specific algorithm called GRPO, or Group Relative Policy Optimization. Instead of a human baseline, GRPO has the model attempt the exact puzzle multiple times in parallel. The algorithm compares these completions, identifying which variations yielded the highest relative reward. Finally, the agent's policy is mathematically updated to favor those winning strategies. GRPO allows the AI to refine its own strategy through comparative trial and error, moving beyond the limits of memorizing a static answer key. Zooming out from the game environment helps clarify the contrast between standard supervised fine-tuning and true reinforcement learning. Fine-tuning is a rigid, static process of memorization, a method that is highly similar to a student repetitively studying flashcards. You use fine-tuning when you need to teach a model how to format output, mimic a specific human style, or learn how to speak based on specific examples. Reinforcement learning is dynamic and experiential. It requires physical balance and constant micro-corrections, much like learning to ride a bike. You use reinforcement learning to teach a model how to act in order to optimize for complex, open-ended goals. In these open-ended domains, success relies on a sequence of logical decisions, rather than just a single correct answer. By integrating environments, reward systems, and comparative algorithms like GRPO, researchers are building reasoning agents capable of navigating the digital world.